Okay, so glad you made it this far. We all made it this far. And to conclude a very nice, interesting day, we have a panel with some really great guests. So, and it was actually a great idea that they had, that everybody sits under their own picture, so you can just see. I don't have to do much to introduce them. So we have Sebastian Riedel from Facebook AI Research and UCL. We have Christos Hadjinikolis from Reply UK. Andy Jefferson, whose talk you've probably seen earlier from Octavian AI, and John McLoone, whose talk you've definitely just cast from Wolfram. So the topic we're going to be addressing is, well, the different tribes in AI and how, how they're connected and what does graph have to do with all that. And I guess we're going to start, a good way to start would be by addressing exactly what are these tribes. And it's, well, if you are into AI in some way or another, I guess you may know this, but not everybody. So actually, the first reaction I got from James, my co-organizer, when I suggested this topic, was like, isn't it a bit controversial? And we're like, well, no, actually, AI tribes are a thing. But instead of me trying to explain what these things are, what I thought was, well, I'll let these people explain that know it far better than I do. So yeah, gentlemen, just take your turns, take the microphone, and just pick your favorite tribe, and yeah, just say a couple of things about it.
Okay, I think even for me it's not that easy, because there's certainly several tribes that I like. This notion of tribes is actually maybe in some of the tribes not as apparent as it is for you right now. So I actually had to look it up. And then so according to Pedro Domingos, I guess there's the connectionist tribe, right? There's the sort of analog reasoning tribe, there's the symbolic reasoning tribe.
Symbolists, evolutionaries,
yes, exactly. And I'd say, and then Bayesian tribe as well. And I'd say I somehow fit into the connectionist, Bayesian, and maybe symbolic tribe. But I'd probably start with the connectionist tribe.
Okay.
So I guess more or less this is about deep learning at the moment, which is this idea of building these neural networks that essentially do everything for you if you just give them enough data. I don't want to go necessarily into technical details, but it's fair to say that in the last couple of years, we've seen sort of amazing results coming out of that line of work. In particular, whenever there is a lot of training data for the particular task that you're looking at, which happens to be the case in a lot of the researchy kind of things that we do in research, which generally doesn't happen to be the case in all of the practical things we want to do in the real world. And so I guess for me, I find it exciting, but I also think a lot of it is missing, in particular prior knowledge and how we get into. And so that's sort of where my symbolic hat comes in. Where I think, obviously, marrying these two worlds, or 5 worlds probably, but I think my focus is on these two, symbolic and connectionist worlds, is quite important. And I guess I'd just like to say I have been, and there is actually, for those who don't know, there is a big community within ML that just looks at this problem and has been looking for maybe the last 20, 30 years in seeing how machine learning and symbolic sort of AI can come together. I'd be curious to hear and understand, maybe also from the other participants in the panel, why, even though there has been this effort for a long time, we think this really hasn't paid off in a way that anything else in machine learning has paid off. And I'd love to get a better understanding of this.
Okay.
Hi, everyone. So if I was to identify myself with the 5 tribes, I'd say I'm closer to an evolutionary as well as maybe symbolic AI. I think that, I agree with Sebastian. It's we're going through some very interesting times. The concept of merging symbolic AI with connectionists, or the connectionist approach. Anyway, it's very interesting. Myself as an evolutionary, and by the way, before I go into that, I think it's best that I explain a little bit about what that is. So when it comes down to the evolutionary tribe, if you want, we're mostly talking about search based solutions, whereby you try to search a solution space for a problem and try to identify a good approximation most of the time of a problem using a variety of techniques, random hill climbing or genetic algorithms. This is part of the things that I apply in my work. But I also appreciate symbolic AI as well. In fact, it was part of what I did in my PhD thesis. And when I think about symbolic AI, my mind goes to formal theories of reasoning. It's the science that has to do with how we reason about the world. And it's an attempt to practically pass on our way of thinking into machines, which would have been ideal if we could do it one way or another. But yes, the fact is that symbolic AI has not been very successful. And therefore we turn too much, or maybe more than we should, on approaches like machine learning, linear regression, neural networks, because they seem to be a lot better at producing the results. I do think that the two could be merged together. I'm also interested to find out what other people in the panel think, and yeah, let's see where this goes today.
Thanks. So I'm personally a connectionist as well. My background is in computer vision and training convolutional neural networks. But I think pragmatic researchers tend to span at least 2 or 3 of these areas. So I use evolutionary algorithms a lot to actually learn hyperparameters for my neural networks. So it certainly requires, or I benefit from having skills in that area. I think the Bayesian, in the kind of sense of Bayes' theorem, is a very interesting way of combining learned data, like observed data and priors. I think that's a very interesting area to start joining up things like connectionist, where we just learn from data, with things like symbolist, where we just have priors. So I think that connectionist thing is starting to plateau. Neural networks are great for computer vision, they're great for sequences, and they're great for reinforcement learning. But within that community, I think there's a realization that the gradient is definitely flattening, and they're starting to look outside of that for things that can improve and enable it to tackle tasks that aren't just computer vision, natural language processing, and reinforcement learning. So I'm very excited to be on this panel.
Thanks. So if you were in my talk, you'll not be surprised to hear that I come from a symbolic background, and a lot of what we're trying to do is to use symbolic background to try and bring all the tribes together. But one point I'd make is that the tribalism actually depends a little bit on how deep you are in the field. That if you are at research level, then the details of difference between the different tribes and the way you go about solving the problems really matters. But as a consumer of AI, or as kind of at, to be using AI for research but without caring about the details, it actually matters a lot less. It's a little bit like if you look at maybe, automotive engineers who are working on diesel and petrol engines. They probably have greatly different background knowledge and skills, and the details of exactly how they design their engine really matter. When you're driving a diesel or a petrol car, it probably doesn't matter that much which tribe you're in. So our aim is to try and automate those kinds of details. These guys are probably at the cutting edge. It matters much more exactly how you search the parameter space to solve a particular problem. These days, I see myself actually as a mix of symbolic and connectionist, because I kind of feel like they're at the opposite ends of the spectrum. And for me, as a user of these tools, I think it's more a question about what's your conceptualization and prior knowledge. If you're data rich and understanding poor, then machine learning models are really great. But they're not the only trick in town. If you're understanding rich and data poor, then symbolic approaches are much better. And I disagree that they haven't been successful. We just take for granted the kind of engineering and science that symbolic maths, which is symbolic AI, has made possible. But that's become so routine to be able to solve equations and solve differential equations and model fluid flow and things like that, that we don't really think of it as AI anymore. When I started, being able to do symbolic intervals was considered AI.
Can you pass it on? So yeah, one simplistic way of summarizing, let's say, the 2 ends of the spectrum would be, well, on the one hand, you have the approach of trying to model everything up front and coming up with a rule-based approach, basically, like, A, if A, then B kind of thing. And on the other hand, you have the approach of trying to find out patterns in lots of data you have gathered. And I kind of guess this is why machine learning has dominated today because basically we have much more data than we used to, and we also have much more computational power, so that makes it easier to find the patterns in the data. And that kind of reminded me of a story. Well, in a previous life I used to do research on this kind of thing as well, and at some point the question came like, okay, so what avenue should we be pursuing? Should we try to model everything, or should we try to learn from the data? And the answer that came from the head of our research group, well, you should try to do both. And that's what we're seeing more and more these days. So, for example, you have more and more top organizations that are finding value in knowledge graphs and trying to actually model the world to some extent. But on the other hand, you have the realization that this can only take you so far, and you need, it's actually a good thing to do, to try to enhance your knowledge graph by getting knowledge out of data. So and we've seen, you know, organizations like Google or Facebook or Salesforce, or, you know, all the big ones that are basically following this approach, building their knowledge graph but enriching them with data that they get out in the wild, let's say. So I was wondering if you can refer to some of the things that you do, let's say, in your day-to-day, in a typical day at work, and what kind of approach you're using for this. Let's start with Christos this time.
So many of the problems I'm working on relate to graph analytics, really. Some of the approaches I use have to do with traversing graphs in a variety of ways in order to find out things about their structure or something else that I'm finding useful for extracting insights from them. Lately, I've been focusing a lot on the development of Monte Carlo simulations, like basically random walks that help me traverse the graphs in a variety of ways to find out things. Other than these, I'm also dealing with problems that have to do with process mining. It's a field that tries to extract something like a finite state machine from monitoring event logs, if you want. There's a very interesting work, by the way, from Facebook. It's called the Mystery Machine. They come up with very cool names at Facebook about the work they do, and so approaches that are mentioned in that paper, and do Google it. It's a very interesting paper. I'm using my line of work as well. It basically has to do with starting with a fully connected graph, assuming that you have a number of states, a finite set of states, and as you monitor events coming in, transitioning from one state to another, you sort of figure out which links in the graph to reinforce and make it stronger and stronger, and which to drop out, and you end up with a good representation of the processes that take place concern those events. All these things rely on evolutionary techniques, really. It's search-based solutions. In terms of tools, I rely on Apache Flink. It's a framework for string processing, but it does have a batch API, and I'm using a lot the Jelly library. It's a graph processing library. Yes, that's some of the problems I'm working on. Andy?
So my research is really focused on building these things we think of as differentiable neural computers. So that's neural networks that learn how to do algorithms, predominantly graph algorithms in our research. Day to day, I'm trying to break down these quite complex things. They're like computers. They're made of many components working together. I try and break them down to work out which part isn't working how I want it to, and then subject that to experimental tests to make it do what I want. So it's very empirical. It's like doing science in a lab, because it's pretty difficult to reason about the neural networks and why they behave the way they do without subjecting them to experimentation. The tools I use, generally TensorFlow, just because that's what I'm used to, not because I have any bias against other frameworks or languages. And the other thing that I find very helpful is a company called FloydHub, which allows us to ship experiments into the cloud to do things like grid search and evolutionary jobs, where we send hundreds of workers to do the same task in parallel to find parameters that work well.
So at this point in my career, I don't work in our core R&D group. I lead a technical services group, go into other organizations and try and solve their problems for them. So rather depressingly, actually a good fraction of my time is dealt with trying to explain to people what's in their data, even though it's their data, and then dealing with the crappiness that's in their data of data sets where people think that -999 is a good way of saying missing and things like that. So an awful lot of data cleaning and preparation and then visualization so they can make sense of it. And then in the middle, we get to do a little bit of machine learning or sort of coupling together different computational techniques to actually get the insights. But I would guess 80% of my time is with the boring stuff, unfortunately. But it does pay.
So maybe I say what I used to do, because I think that relates to this topic. So I've been spending a lot of my research time in the past trying to automatically extract knowledge graphs of sort from text. And we've done all kinds of machine learning to do this. Now, today, I think that's probably not such a good idea, and I try to spend most of my time getting rid of knowledge graphs in that context, not because I have a problem with knowledge graphs, just because I have a problem with the idea of mapping language to knowledge graphs that are usually relatively noisy and miss a lot of the information that I have still in the original text data. And we have seen now evidence in, at least in NLP, for knowledge representations that aren't maybe necessarily good for users to look at, but who've been making other downstream tasks so much better than, I guess, the knowledge graphs of the past that we tried to build, that this is currently, I think, one of my focuses. So I guess to name an example, and I think for most people here that it's probably not that meaningful, but I'll try to explain it quickly. So there's something called Elmo or BERT. There are actually two new models that just came out in ML and in natural language processing called Elmo, and one called BERT. And I'm sure we're going to see Cookie Monster and Big Bird and all of that pretty soon as well. So, and what they do is they essentially take a big data corpus and learn embeddings or word embeddings in the way that Word2Vec would do it, and maybe some of you know that. But instead of just doing that, they also use the context around the words to produce different vectors for the same word in different contexts. And this is a relatively simple concept, which has so dramatically improved results across so many NLP tasks that now I've started to rethink how I think we should think about knowledge representation, at least from a downstream sort of ML point of view. It's like if you have an ML model that you want to do something on data and you need a knowledge representation, I think we should start rethinking of what we feed into these models based on the experiences that we've seen essentially in the last year. So that brings me to what I do right now, is to essentially better understand how these kind of approaches can work as a knowledge representation / knowledge transfer mechanism from one domain to another, and how that can be integrated with knowledge graphs in one way or another. And I guess the tools that I'm using for that whenever I get to code are things like PyTorch. Not that I have a particular reason to use that. I think I would be allowed to use TensorFlow, but PyTorch I think is better. And then essentially standard deep learning things on top of that.
Okay. And well, as you all know, there has been a quite influential already, I would say, paper that came out from some people in DeepMind and Google and the University of Edinburgh. And what they're trying to propose in that paper is a sort of unifying framework, let's say, of how one can use graphs as a means of representing background knowledge, let's say, and somehow, adding to the machine learning process. And I wonder what your opinion is on that, and whether you think this can work in some way, or where this could lead in any case.
That was well timed. That's the paper I talk about in my talk today.
Yes.
So the paper on relational inductive biases, I think it's got a slight schizophrenic character, because they have this start section where they talk about Chomsky and philosophy and understanding biases, and then they have another section with results, which really doesn't have a lot to do with that, and they just predict like how models of physics involving chains and balls will work. So they don't, as a kind of pragmatist and an empiricist, they don't back up the first calf with any empirical data. It's more of a philosophical position. Having said that, I completely think they're onto something with graphs being a way of representing knowledge that is incredibly valuable if it can be used by machine learning and neural networks. I'm not sure they really showed that synthesis that we'd like to see. One of the reasons I think graphs are so powerful is because they're homomorphic, right? That all graphs look the same, and so if you can start to interpret that symbolism, the graph symbolism with machine learning, then there's scope to start to tell the machine some truth, as opposed to requiring it to learn truth from many thousands of examples. And that's what I think is really exciting about the concept they put forward.
Thanks. So the symbolic representation I was talking about throughout my talk, actually, of course, if you look at it from a certain perspective, is a graph representation, because every one of these symbolic expressions that I showed is actually a tree with the outer wrapper that represents the type of object being the root node and the arguments being the various branches below. So in terms of representation of things in graph format for neural networks, we're already been heading that route for 30 years. There's still a lot of challenges actually to make it do anything useful, which not least how do you extract the features and learn against graph features usefully. One of the directions we're heading towards, which we're still a few years out from, is to try and take the computational tools that we have and make them accessible as layers within neural networks. At the moment, we represent the basic current knowledge of neural networks in about 30 different layers. So there's some very elementary things like connected layers, which are just matrix multiplication. You've got convolutional layers, which are doing sort of matrix convolution with discovered kernels. There's no reason why you couldn't have layers that are doing high-level graph operations, which then might make some of these learning operations on graph data actually much more exciting. The problem comes in actually being able to do that efficiently and to run them on GPUs so that things converge within our lifetimes. And that's where all the engineering comes in. It's why we can't do this today. We could probably do it theoretically now, but it would run so slowly that it's of no interest. But it's certainly a direction that we're exploring of graph neural networks. But ask me again back in 2 years, and maybe I'll have something to show.
Okay.
So, in general, I agree both with John and Andy, or with Andy in terms of whether the paper specifically has been successful in terms of showing the synergy between the two practices that we hoped for. At the very least, I think that they are on the right track. I think that it's a good path to be on. And I want to take a very simplistic approach to it and simply say that it's not enough to rely on one tribe to try and solve a problem, right? So far, our field, we haven't been very successful in terms of achieving anything close to general AI, but we have been very good with solving specific problems. And if we are to ever generalize to something more successful, I think it will come from a synergy like that. I like to think of it in terms of, so when I try to explain what I do to my mom, it sometimes comes down to describing what machine learning is. And I have this very simple example where I talk about the aspect of dreams and whether people believe in dreams. Like I don't believe if I see a dream that it's going to materialize into something bad. So for example, if you ask somebody if they've saw a dream of them driving to work and having an accident, if they will drive to work next day, most people are going to say, yeah, they'll do it. But if you are involved in an accident and later day you see a dream and again you're involved in an accident, are you going to drive to work again? And if you do it the second time, are you going to do it the third time? I mean, this is more or less machine learning if you think about it. It's based on experience. If it happens again and again, you don't really need to know exactly why it's happening. It's just that you won't do it because it's been happening again and again. You don't need a reason to explain it. On the other hand, we don't jump in front of cars when we cross the road. We try to avoid them, not because we've been hit by a car before, simply because we know that it's very likely that we'll die if we do it. And it's not based on machine learning, it's not based on empiricism, it's based on logic, right? So I think that there's a lot to gain by finding ways to achieve some sort of a synergy between the two. In a past life as an academic, I worked a lot on a field called Argumentation Theory. It is something that stems from logics. It has to do with non-monotonic reasoning. Anyway, it is a very interesting field that has to do with how to model knowledge in a way, using graphs, in a way that allows you to deduce what is true about the world. On its own, it hasn't been very successful, but I think that if it's somehow linked and assisted by machine learning techniques, approaches explained in that field could be very useful and could prove to be very successful in terms of achieving something close to what we refer to as general AI.
Right. So this paper is actually really good for a couple of reasons. Like the first one is that so DeepMind does amazing work. One thing they're also really amazing at is PR and that's a great skill. Like I'm not talking it down. So I mean it's fair to say that what they describe there has been a part of a research community for a long time that all have been working essentially on this idea, and there's been, I mean, they're cited, so it's not a problem. But I think one thing that has been holding back that community, which I was or am a part of to some extent, is just a lack of a sort of marketing team, right? In a way that DeepMind or Facebook has it in a way, and because partly what they say in this article is relatively obvious in the sense that so basically what they're saying is we need biases, and that a lot of data that is out there, that this data is somewhat relational or graph-based, and to do better on that data, we need to sort of take that into account and build models that know about the structure. Yeah. And that's really obvious in the sense that, for example, natural language processing is all about processing chains of objects, namely words that follow each other. And pretty much every architecture or every neural architecture that we have on it is sort of capturing this in one way or another, and hence is using the power of graphs or relations to bias the model to use less data and be more efficient. So in a way, they just have a very good way of presenting that and putting a blog article around it and writing a nice write-up about it, which is great. I don't want to talk it down. The other thing that I find interesting in that article is that I think there are two things about graphs in AI. Like one thing is a lot of data inherently relational? And when we process it, should we capture that information? And the answer is yes. I mean, clearly, Facebook has a big graph of things that we always use the structure of that graph to make any kind of inferences. Same with language or with images, right? There is a structure which you can represent as a graph, and then you should be using it. I mean, the other question, though, is, are discrete graphs a good latent representations for agents to model the world and make predictions and capture their observations sort of latently? And I'm still not sure about this. This is partly what I said in the previous bit. Putting text into a discrete knowledge graph has a lot of problems, and I'm not fully convinced that it's the best way of going about it. I mean, Paul is just sitting there wanting to say something. I don't know when you.
I wanted to really ask you about that. So do you believe that?
Wait. Let me get you a microphone, because anyway it's time for audience questions. So you have a tendency for doing the first one.
Yeah,
so there you go.
Just keep going. I have lots of questions. So do you believe that the outcome of for most downstream tasks, are you under the hypothesis that some sort of other kind of latent representation is going to be way more useful, and actually the only reason we should be generating graphs is for people and not for machines?
Almost, yeah.
Yeah.
So I think I would qualify that in the sense that I believe that even the sort of non-graph structures that will have some form of relational notion in the sense that there will be entities, but I think it will be not a discrete graph, right? There will be maybe edges that are represented in vectors, right? All of that, and but not necessarily a discrete knowledge graph. So I think that's the main thing I'm saying. But I'm not even sure about any kind of graph structure, just based on the success we've seen with Elmo and Bird. So, I mean, I'm overfitting to that example right now because it's so recent.
Yeah,
but
hypothesis is that my hypothesis has been that graphs, actually knowledge graphs, are useful consumption devices for people.
Yeah.
Right? Because I think in Facebook and I have contacts lists and, right, I like my little table on the side of fantastic for people, fantastic for developers, right? Developers think that way. But I don't think machines actually do, right? Machines think in high dimensional, large matrices. I think.
I completely agree. I think the other thing is that with like Facebook and other graphs, because they're sort of human generated, they're also somewhat correct in a way, right? So every time we have a graph that somebody's building, I'm all up for it. It's sort of emerged naturally and it's useful. But every time we say graph should also be the thing that machines use for communicating internally or working, that I don't agree with. Yeah.
So first of all, I have to say that most of all of this stuff I feel like is quite a lot higher above my head than what I normally have to deal with. I deal with very standard sort of machine learning type AI, and I'm moving into the knowledge graph space. But what you've just, this discussion that you've just had there strikes me as very informed by organizations that have huge amounts of data, because those embedding models themselves also are reliant on huge amounts of data to perform. Whereas the more, I don't know if deterministic is the right word, but I think you mentioned it, that ability to tell a machine something that we already know means I don't have to have the data volume to teach the machine that part. And that's why I'm kind of, that resonates with me to say you have to combine the methods to get somewhere. Is that fair?
That sounds right to me. Like, I don't want to hijack this, but so I in a way, the way that I see what you just said is that, or the way that I interpret this is that I think we need to have ways to bias machine learning models to do more with less data. A good way of doing that is through a graph representation, because we know how to represent things in graphs. And if we can tell the machine, look, operate with this knowledge, I'm all for that. But if we say the machine should internally work like a graph and do sort of symbolic reasoning on top of it, I don't necessarily agree.
Other takers?
So, to me, it seems like to some extent it comes down to an HCI problem, a human-computer interaction problem, right? And it has to do with finding a way, ideally, to have machines communicate in a way that humans would have been able to understand. If we can somehow solve this problem, then we wouldn't have to worry about separating the two, which we seem to be doing more now because of efficiency problems. This field called argument mining at the moment, it has not attracted a lot of attention. But it's the study of inferring arguments in the form of inference rules, premises, and some form of conclusions, so the trees that John was talking about before, from natural language processing. Ideally, this is a way to avoid telling the machine how to use data or how to reason about the data that you give it. It's the machine on its own reading a document and being able to extract information from it. When I was talking about a synergy between symbolic AI and machine learning, I was thinking about a case where we use machine learning to generate these inference rules in a way, however, that would be, I don't know, obviously this is an open problem, but I'm just referring to a case where we would enable machines to create rules about the world, infer arguments about the world, and then use existing techniques to reason about the knowledge they have. If we're talking about a knowledge graph, for example, it could be the case that when you apply some sort of a traversal algorithm that tries to identify subgraphs that represent different versions of truth. Grounded truth, for example, could be a subgraph. If we're talking about a graph where everything is an argument, edges could be, for example, attack or defeat relationships between arguments. And you could try and identify subgraphs with certain properties, which would mean that if they comply to this restrictions that you would put in place, you will have identified some sort of a grounded truth within the limited search space that you've generated, the universe of knowledge that you have. These are the kind of things that I have in mind. I don't know if that answers your question to some extent.
I'll give a slightly different perspective on it. The question about, from a compute point of view, about which is better is to some extent just solvable. It's an efficiency question. It's solvable with more CPU power. You can always get more with more CPU power. Now, it might be that the orders of magnitude are enough that it's worth getting that right, and I'll leave that to experts to worry about the details there. But you can't ignore that human side of it, because while a lot of the compute power issues can be scaled with just more CPU, you can't scale the human side of the equation with more people, because more people are not more intelligent than one person. So at some point, the bottleneck in some of these things becomes the human ability to comprehend what they're telling the computer to do, or providing the information, or checking the information's right. And if, in fact, the one representation is better for a human to understand, that is not an ignorable issue. It's a big deal to make sure that we do the right thing, even if that means a bit more CPU power.
I'll take this on a slight tangent. There are some things, I think, where we can't actually tell the computer what the truth is, because as humans, we often struggle. A simple example from image classification is things like, is this a husky? Is this a spaniel? Because there is no Platonic definition. But as humans, we're used to a world where we look at it and we're like, well, yeah, it's probably a spaniel. It hasn't got floppy ears, this particular spaniel, but it's otherwise spaniel-y enough. Or this husky does have floppy ears, but it's a husky. And you have this argument from kind of, I'll know it when I see it. And for a lot of cases, the world is like that. For other cases, like maths, it's not like that. But we can only get so far if our restriction is purely constructing a kind of semantic, this is what the truth is. So I think the exciting power of neural networks is their ability to imitate that human behavior. And for me, an ideal solution combines the two. I have the same problem that you talked about, where I want to tell the computer, the AI, some stuff. I don't want to, worst case, I don't want to be sat there constructing training examples where I just repeat the same thing over and over again to force into its brain the truth. I'd love that. But at the same time, I don't want to restrict it to a really rigid logic that can't encompass the world as we understand it.
So argumentation theory probably is an answer to that question, because as a field of research, it attempts to bridge the gap between humans and computers. It tries to enable machines to reason in a way that is amenable to human understanding. Basically, if I'm to give you an example, let's suppose that we're talking about an argument, okay, and that argument has to do with you see birds, you can identify birds, you've seen birds fly many times, so you know that if something is a bird, it probably flies. So if I tell you that Tweety is a bird, you will infer that Tweety can fly. But the thing is, you don't know that Tweety is a penguin, and penguins don't fly. So all of these things that I just talked about can be represented as arguments, and the relationships between them can be represented as attacks. Okay. Now, this generates a graph, and there are formal theories that you can apply on this graph that will allow you to deduce within this graph what is grounded truth. Of course, it is a limited universe, okay? You don't know everything about the world, but within the world that you've just defined, right, you know what is true and what is not true. The power behind this approach is that it is amenable to human understanding. You apply some sort of a graph traversal algorithm on this graph. You find out something about it, maybe a subgraph that has some properties relevant to some acceptability semantics, grounded, credulous, whatever. And this can be returned back to humans, and we will be able to understand it because it's just going to be a node in a graph, and you will be able to just click on the node, open it, and see what's inside, and it's just going to be an argument that you can read. The problem with these things is that you need to feed the system with these arguments. Arguments cannot be extracted from natural language. This is where machine learning can come in and help. If we could find a way to read natural language and enable machines to extract arguments from it, then I think we would be very close to achieving what you just asked for.
Yeah. So I probably disagree with that in the sense that, so partly I'd say, in the sense that I don't think agents need to actually operate in this way, partly because I don't think that we operate in that way. But I do think agents should be able to explain themselves in that way that you just described. And what that means, I think, for explanations is that there has been actually some real interesting work recently, things like Lime and Anchors, for example, if you want to look up something, essentially methods that take black box machine learning models and try to extract explanations from these, in the sense that these explanations will look like maybe a decision tree or maybe a graph, and they will kind of match the behavior of the deep neural network they try to explain, but by no means is the deep neural network doing exactly what the decision tree does. But still, these explanations work in the sense that users of the machine learning models can either trust the model, they can improve the model, and they can do various things that you would do with an interpretable, fully transparent type of model. And to me, that's the right way forward. In the same way that I think the way to... So we should be able to talk to the agent using, say, natural language or relational graphs, and the agent should somehow consume that and make use of that knowledge, but we don't want the agent to actually operate in this way. In the same way, we don't want the agent to explain things exactly in the way that they operate, because I also don't think we do this, right? Like we try to communicate what we do, but actually we don't even know what we do. But it's still good enough in the sense that it helps others to trust us, or it helps others to improve our behavior. So I think we should disentangle what happens within the agent to how the agent communicates back and forth.
Okay, well, we've already quite a bit over time, so I guess we'll wrap it up here. Thank you.